welcome to This Explainer. We are completely skipping the pleasantries today and plunging right into the absolute limits of astrophysics. We're talking the emptiest, coldest, and densest parts of our universe. Let's go. So let's start with a very basic question. Why is space a vacuum? Why is it actually completely empty? Well, the physical mechanics behind the emptiness of the cosmos actually hold a surprisingly violent answer. You see, space is an almost perfect vacuum. But to really understand the cosmos, we need to completely toss out the analogy of that dusty machine sitting in your closet. It's not the same thing at all. Household vacuums rely on differential air pressure. Space, on the other hand, is empty simply because gravity is the ultimate runaway hoarder. Over billions of years, it relentlessly pulls gas and dust together, aggressively evacuating the vast spaces in between. It's basically sweeping the universe clean. And because gravity is so relentlessly clumping everything together into stars and planets, the average density of the entire universe is mind-bogglingly low. We're talking just 5.9 protons per cubic meter. It gets even emptier out in the vast cosmic voids. Intergalactic space literally has less than one single atom per cubic meter. You just cannot simulate that level of sheer emptiness anywhere on Earth. All right, moving on to the quantum chill, places even colder than deep space itself. It's actually incredible to think about, but right above our heads on the ISS, NASA's Cold Atom Lab chills atoms down to 1/10,000,000th of a degree above absolute zero. That is miraculously 10 billion times colder than the natural vacuum of deep space. Just let that sink in. At these extreme temperatures, atoms form what's called a Bose-Einstein condensate. Basically, they slow down to almost a complete halt, they physically grow larger, and, bizarrely enough, the entire cloud shares a single macroscopic quantum identity. It's like they all become one giant superatom. And the microgravity of space makes this weird state of matter so much easier to sustain and actually study. Let's completely flip the script now. Welcome to the infinite crush, black holes. You probably already know that when a supermassive star's core collapses into a singularity, the density becomes infinite. It bends space-time so severely that the escape velocity actually exceeds the speed of light at the event horizon. But looking at the relativistic physics here is where things get really wild. Unlike classical Newtonian orbits, where you can, essentially orbit forever, near a black hole, high-energy objects completely bypass that local minimum. They just plunge straight in and get absolutely shredded by infinite tidal forces. No way out. Because of the extreme warping of space, the orbital potential develops this weird extra hump. This means that inside 3 times the Schwarzschild radius, stable circular orbits simply cease to exist entirely. Actually, scratch that. They don't just cease to exist. They become physically impossible. You either have the energy to escape or you fall in. There is absolutely no middle ground here. And hey, we aren't just guessing at the math. LIGO data captured the exact moment 2 black holes spiraled into each other and merged, literally allowing us to measure the ripples of infinite density colliding in real time. It is a massive game changer for astrophysics. Okay, so how did all of this get here? The origin, from fog to voids. To answer that, we're zooming way out, 13.8 billion years out, which brings us to the ultimate cosmic extreme, the Big Bang. This was an initial singularity where the laws of physics, as we know them anyway, completely break down. You see, the early universe wasn't full of empty voids. It was a dense, incredibly uniform fog of energy. Around 300,000 years in, it finally cooled enough to become transparent. Then, over billions of years, gravity took over the driver's seat. It clumped that fog into galaxies, hollowing out the vast, sparsely populated cosmic web we inhabit today. Incredibly, we can actually still see the afterglow of that initial dense fog clearing. It's the cosmic microwave background. And because the universe has been rapidly expanding and cooling for nearly 14 billion years, that very first light is now sitting at a chilling 2.7 Kelvin above absolute zero. But here's the kicker. That expansion isn't stopping. In fact, we know for sure it's accelerating. Astrophysicist Jackie Faraday points out that because the universe's expansion is speeding up, gravity will only ever congregate local matter. This basically ensures that the broader cosmos will remain mostly vacant and become increasingly isolated. As she so perfectly notes, it sounds so lonely. So think about this. Billions of years from now, those cosmic voids will stretch out so incredibly far that light from other galaxies literally won't even be able to reach us. How will future observers even know the rest of the universe exists? Will they look up into the night sky and assume their local galaxy is all there is to reality? It really makes you wonder, doesn't it? Thanks for joining me on this explainer, and keep questioning the extremes of our universe.